In last class, we discussed about mutual inductance. At the end of the lecture, I told you that you basically have to remember three formulas from the last lecture. First one is basically the definition of mutual inductance, that N1 phi 1, that is flux passing through coil 1 into number of turns of coil 1, that is total flux passing through coil 1, is equal to a constant M12 into current flowing through coil I2. This lecture is in continuation with the previous lecture, so please follow the sequence. This expression was derived because suppose we have a coil here. Let me call this coil solenoid S1 with N1 number of turns. And let's suppose we have another coil here. Where you are connecting a voltage source over here. Because of that, a current I2 flows here. So it has N2 number of turns. Solenoid S2 with N2 number of turns. When you connect a voltage source here, a current I2 flows. Because of this current I2, this solenoid produces a magnetic field B2, where you know that B2 is equivalent to mu naught small n2 into I2, where small n2 is number of turns per unit length, into current I2 flowing through the solenoid. This is magnetic field produced by this. Now because of this magnetic field, this solenoid will produce a flux, and a part of that flux will link this coil as well. Now how much flux produced by this coil, this solenoid S2, how much flux produced by solenoid S2 will link solenoid S1, that is N1 phi 1. That basically is proportional to current I2. More the current I2 here, more the magnetic field here, more the flux here, more flux will be linked to this coil as well. So this is proportional to I2. In addition to that, the flux of solenoid S2 linking solenoid S1 also depends upon the orientation, depends upon the distance between the coils, depends upon the area of the coil, length of the coils, and so on and so forth. In short, it depends upon the geometric property or geometric configuration. Fine. That's what is known as mutual inductance. So this mutual inductance basically is a function of orientation of coils as well, dimension of the two coils or dimension of the two solenoids, as well as the orientation of the two coils. Fine. Okay, let's move ahead. Wait a second. Okay. Thus what we mean to imply here is, when current flow through this coil, because of current flow through this coil, it produces a magnetic field. Because of that magnetic field, it produces a magnetic flux. That magnetic flux links solenoid S1 as well. So there is a flux through solenoid S1. How much is flux? N1 phi 1. Now if I ask you, what is the voltage induced across this solenoid S1 or coil S1? If you remember Faraday's experiments, when current through one of the coils changed, there was a deflection of galvanometer in another coil. This is the same experiment. Now the flux through this coil is N1 phi 1. What is voltage that will appear across this coil S1? Do we have an expression for this? Yes, we do. We know induced EMF E1 in solenoid 1 is equivalent to minus from the Lenz's law n1 number of turns into d phi by dt, where phi is the flux. So induced EMF that will be induced across this coil is E1 equal to minus N1 d phi by dt. Or I can slightly make a change over here, keep minus as it is, get this N1 inside, this becomes d by dt N1 phi 1, or this becomes E1 is equivalent to minus d by dt of, what is this N1 phi 1? N1 phi 1, we know this is now M12I2. We already discussed it yesterday. Mutual inductance of 1 with respect to 2 is a constant. It depends upon the geometric property, its length, its number of turns, its radius, and the orientation. Since these things are constant, they does not depend upon, these are not function of time, I can take mutual inductance out. So this becomes E1 is equivalent to minus M12 d by dt of I2. This is basically the Faraday's law. As per this statement, the induced EMF in coil 1 is equivalent to a constant, that is mutual inductance, times d by dt of I2, that is rate of change of current over here. You remember the voltage will be induced in this coil only when this will experience not the flux but change in flux. You remember you should have d phi by dt. Here voltage will be induced when this coil will experience change in flux. How will this experience change in flux? Where is the flux coming from into this coil? The flux is coming from here, solenoid S2. In order for this flux through solenoid S1 to be changing, flux produced by solenoid S2 should be changing. How can this S2 produce a flux which is changing? It will produce a flux which is changing only when the current flowing through this solenoid is changing. So if this current I2 changes, you have di by I2 by dt. When current I2 changes, magnetic field produced by solenoid S2 changes. When magnetic field produced by solenoid S2 changes, so flux produced by S2 changes. When flux produced by S2 changes, that means flux linking S1 changes. When flux linking S1 changes, we know that it will have an EMF induced across it. Fine. So now tell me, if you have two coils which are placed in vicinity of each other, and there's a current flow through one of the coil where current is changing, and you want that voltage should be induced in another coil. Like in this case, you have solenoid S2 where current I2 is flowing, and you want that EMF should be induced across solenoid S1. Should the two coils have high mutual inductance or less mutual inductance? The two coils should have high mutual inductance. That means the flux linking this should, almost all of the flux should link this coil. The more the flux produced by this linking coil S1, more will be the EMF induced in this coil. Fine. Okay. Next we move on to self-inductance. Now let us suppose we have a single coil here now. Yesterday I told you the difference between mutual and self-inductance. I have a single coil over here. This is connected to a voltage source here. This means a changing AC voltage source. We'll study this in the next chapter. You have a solenoid n number of turns. L is length of solenoid. Small r is radius of solenoid. Right? A current I is flowing through this solenoid. If you remember yesterday, we defined inductance basically as, we defined inductance L of a coil as the total flux through a particular coil. Here number of turns is N, flux is phi. We defined inductance as the total flux through the coil N phi per unit of current. N phi divided by I. Remember this? We defined self-inductance as the total flux through the coil per unit of current. That is N phi divided by I. Or we can write this like total flux N phi through a coil is equivalent to inductance L into current I. If this current is more, flux through this coil is obviously more, because magnetic field will be stronger, so flux will be more. If current is less, magnetic field will be weaker, so flux will be less. Total flux is proportional to current and a constant L. Yesterday, we derived the expression for mutual inductance between two coils M12 and M21. Today, I want to derive expression for the self-inductance L. I will use same concept that I used in last class. Let's take it here. Can't I write this N phi is equivalent to Li here? N is number of turns, phi is flux. I know what is flux passing through this. Flux passing through this is magnetic field B into area A is equivalent to L into I. If suppose L is length, N is total number of turns, small n is number of turns per unit length. I can write this total number of turns as number of turns per unit length into length L. Also, I know magnetic field B produced by this solenoid is mu naught N I. Area of this coil is pi r square is equivalent to L into I. You can take this I and I out. So you get expression for inductance. Inductance L or self-inductance L is equivalent to, write mu naught N and N becomes N square pi r square into L. This is expression for self-inductance. As discussed yesterday also, self-inductance is not a function of current. It does not depend upon current. Self-inductance does not depend upon voltage. It depends upon the geometric parameters. It depends upon the length, it depends upon the number of turns, it depends upon the radius, and it depends upon constants, obviously. If this solenoid had been kept on an iron core or on an iron material or any other material, in general, we would have expressed this as inductance L is mu naught mu r, where mu r is relative permeability, n square pi r square into L. Fine. Now the question arises. Since you are connecting some voltage V over here, because of that voltage V, a current I flows through the solenoid. Because of that current through the solenoid produces a magnetic field, mu naught Ni. Because of that magnetic field, it produces a flux, and that flux is linking the same coil. And how much flux will pass through this coil? Per unit of current flowing, total flux, you call that as self-inductance L. Now suppose if this current I is changing, this is not a constant current, this current is changing. If say this voltage V is changing, that is what basically happens in alternating currents. We'll discuss that in next chapter. Suppose this voltage V is changing or varying. When this voltage V is changing, this current I is changing. When this current I is changing, the magnetic field produced by this solenoid is changing. When magnetic field produced by this solenoid is changing, so flux produced by this solenoid is changing. When flux produced by this solenoid is changing, the flux linking this coil is changing. Now you remember Faraday's law? You have a coil and that coil is experiencing a magnetic flux which is changing, or you have a coil which is experiencing a changing magnetic flux. What happens to a coil which experiences a changing magnetic flux? An induced voltage is developed inside the coil. A voltage is induced inside the coil. Remember that? And that voltage, induced voltage, has a polarity such that it opposes the cause which is producing it. If here current was increasing, so flux was increasing. Because of that increasing flux, here a voltage will get induced. That induced voltage will produce a current of its own, or will try to produce a current of its own, which will try to decrease this current. If current was decreasing, that flux will try to increase the current. If flux was decreasing, current will be induced such that that will try to increase the flux. If flux was decreasing, current will be induced which will try to increase the flux back. Again here we know from Faraday's law that E is equivalent to minus N d phi by dt, or I can write this as induced EMF E is equal to minus d by dt of N phi. But we already know this N phi is equivalent to L into I, so I can write this as minus d phi by dt of L into I, or I can write this as minus, I can take L out because L is constant or L is independent of time, di divided by dt. The expression that we have obtained here is E is equivalent to minus L di divided by dt. That is, if there is di by dt is change in current. If in this circuit, if this current I is changing, you have di by dt, there will be a voltage induced in this coil. According to this expression that we have obtained over here, this expression says E is equivalent to, where E is induced EMF. Induced EMF in this coil is equivalent to minus L di by dt, where di by dt is the rate of change of current. That is, if you have a solenoid in which current I through the solenoid is changing or varying, so you have di by dt. You will have an induced EMF in this solenoid, and that induced EMF will be such that it will oppose the change in current. If di by dt is positive, that is, if di by dt is increasing, if current is increasing, this induced EMF will be such that it will try to decrease the current. If current is decreasing, this induced EMF will be such that it will try to increase the current. Now tell me, had this been a constant or DC voltage source over here, so this V was constant, I was constant. If I was constant, di by dt was 0. When di by dt was 0, E was 0. That means if you have a constant voltage source over here, this current will be constant, so there will be no rate of change of current, there will be no change in current. When change in current is 0, so induced EMF here should be 0. You can explain this also from the Faraday's law. This is basically another form of Faraday's law. According to Faraday's law, if this voltage is constant, this current is constant. This current is constant, so magnetic field produced by this is constant. When field produced by this is constant, so flux here is constant. When flux here is constant, that means there is no change in flux. When there is no change in flux, there is no induced EMF. There won't be any induced EMF here. Fine. This induced EMF, here in this case, EMF is induced in the same coil in which the flux is changing. Here flux through this coil was changing and that flux was linking this coil. So because of change in current here, EMF was induced here. You call that as mutual inductance. But here, current is changing or flux is changing through the same coil, and the same coil has a voltage induced across it. That is why this inductance is known as self-inductance, and the voltage induced here in this coil is known as self-induced EMF. It is self-induced EMF. And what is the direction of self-induced EMF in this coil? Will positive be on this side or positive be on this side? It will depend upon the slope of current. If this current is increasing, so this will produce EMF such that it will produce a flux. That flux will try to decrease this current. If this current is decreasing, it will have flux. That flux will produce a voltage that will produce a current to increase this current. So induced EMF here will be such that it will oppose the change in this current. Now let me explain one more thing, one last thing over here. Suppose you have a solenoid over here, we have a switch over here, and I have a voltage source over here. Initially, when the switch is open, what is current through this solenoid? Current through this solenoid is 0. Or current through this inductor. You can call this inductor as well. Current through this inductor is 0. Now suppose you are closing the switch. What was current initially here? 0. Now when you close the switch, this current will start to increase. Initially current is 0 and it will gradually begin to increase. That is, current is increasing or decreasing. When you close the switch, current will begin to increase, and then it will reach a particular value, constant value. When this current, when we close the switch and current starts to increase, that means there is change in current. Just now we discussed that induced EMF E is equivalent to minus L di divided by dt. This coil will have some inductance. We calculated just now. We calculated inductance of a solenoid. This has some inductance, and there is di by dt because current is increasing. So voltage will be such that here it will oppose the current. What is happening to current? Current is increasing. So there will be a voltage that will try to oppose the current. That will not allow this current to increase. Then how does this current increase in this? Because of the voltage source. I will repeat this, as soon as you close the switch over here, current would have started to increase. But when current starts to increase, that is, there is change in current. Because of change in current, there is a voltage induced here across the inductor, and that voltage will try to oppose the increase in current. In order to oppose that opposing voltage over here, energy has to be spent by this voltage source V. This voltage source V will have to spend some energy. Against this voltage, this E voltage will be induced here. This voltage is opposing, otherwise current would have started to begin here in this direction, but this will oppose the current. It won't allow this current to increase. But in order to allow this current, in order to push this current through the circuit, this voltage source V will have to put in some work. And how much work will this voltage source have to put in to establish this current? This voltage source will have to put in some work against this voltage E. So what is rate of work done? What you call as power. How much power has to be supplied by this voltage source? It depends upon the opposing voltage. Opposing voltage is E and current is I. So rate of work done, or what you call as power, dW by dt, is equivalent to the opposing voltage, its magnitude, E, into current I. You remember this or not? Power P is equivalent to V into I. I am using that expression over here, where V is voltage, E is voltage over here, I is current. Or dW by dt, rate of change of work or power, modulus of E is L di divided by dt into current I. If we want to calculate total work done, W will be integral of dW from this is equivalent to dt goes integration of L I di, or total work done W is equal to, where integration is from initially current is 0 and finally there will be a constant current. Let's suppose that constant current is I, steady state current, or final value of current is I. Work done W is equivalent to L is constant, integration from 0 to L I di, or work done W is equivalent to L. This is integration of x dx. So this is I square divided by 2, limits are from 0 to L, or that is work done W is equivalent to 1 half of L this is 0 to I, 1 half of Li square. This is the work done. This is the work done by this voltage source in order to establish current I in this inductor. But now your question should be, sir, what happens to this work done by this voltage source? In case of a resistor, the energy supplied by battery gets dissipated as heat. What happens to this work done W by this voltage source over here? This work done by the voltage source in establishing current I through an inductor of inductance L is equivalent to 1 half of Li square is stored as the magnetic energy in the magnetic field of solenoid. That is, the work done by this voltage source V to establish current I through this inductor L gets stored as the potential energy, magnetic potential energy of this solenoid. Or in other words, the work done by this voltage source to establish current I through this inductor L is stored in its magnetic field. Energy is stored in the magnetic field of solenoid. You remember when you connect a capacitor, that energy gets stored as electric field in the electric field of capacitor, 1 half of CV square. For capacitor, energy stored U was equal to 1 half of CV square. For inductor, energy stored U is equal to 1 half of Li square. In capacitor, this energy gets stored in electric field between the plates. In inductor, this energy gets stored in magnetic field of the solenoid, or magnetic field of the inductor. Fine. So in last couple of lectures, we have discussed about the concept of inductance in general. Then we discussed about self-inductance and mutual inductance. We derived expression of mutual inductance for a simple case, and we concluded that mutual inductance as well as self-inductance are independent of current or voltage. In fact, self-inductance as well as mutual inductance, like resistance and capacitance, are property or depend on the geometric properties or geometric dimensions, and mutual inductance is in addition a function of the orientation of two coils. And finally, we calculated the energy stored in the magnetic field of an inductor, where we found out that in order to establish the current through an inductor, some work needs to be done, and that work gets stored in the magnetic field of the solenoid. In next lecture, we'll discuss about generator. How does a generator work? What is the construction and working of generator? This is all about today's lecture. Thank you.